Hello, welcome to this video. And today we're gonna find this sum for all natural numbers n. So we have the sum as I goes from 0 to infinity of n minus I, choose I. And this might be a bit confusing. This might seem to be confusing in how do we approach this problem exactly. Might be a bit confusing to see how we exactly do it. So let's try to get an intuition from Pascal's triangle. Because Pascal's triangle gives us exactly these choose numbers. So the 0th row gives us 0, choose 0. The first row gives us 1, choose 0, 1, choose 1. Then 2, choose 0, 2, choose 1, 2, choose 2. And so on. And the rule for Pascal's triangle is each number is the sum of the two above it. And you can think of the empty spaces as zeros. So 1, 1 plus 0, 1, 1 plus 0. 3, 2 plus 1, this 3 also 2 plus 1, 2, this 2 is a 1 plus 1, and so on. You can continue filling this downwards forever. And if we try to figure out what and sum means, that let's get an intuition for it. So let's say for n is equal to 4, we're starting at 4, choose 0, and then we're moving to 3, choose 1, then 2, choose 2, and then the rest of them are zeros. Because remember, the empty spaces are just zeros, and we get this 1, 3, 1. 1, 3, 1, which sums to 5, but if we look at the shape, we look at its shape in the triangle, it's a diagonal. And if we start from row 5, we'll have this 5, choose 0, 4, choose 1, 3, choose 2, and so on, and so on. So it seems like we're having these diagonals on Pascal's triangle. And if you actually go out to figure out these sums, you find out for 0, it's just 1. For 1, it's 1, then the rest are 0. So 1, 1. Then it's 1 with another 1. So that's 2. So for this 1, 1. Then 2. Then we have this 1. And then you move on over and diagonal plus 2. And then the rest are zeros. So we get 3. And then we suffer for it's 5. For 5, we look 1 plus 4 plus 3. It's going to be 8. And it seems like these are the Fibonacci numbers, where the Fibonacci numbers are defined recursively, very similarly to Pascal's triangle, where each number is the sum of the two previous numbers. The two initial values are 1. 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3, 8 is 3 plus 5, and so on. And so now we know what we're trying to get at here are just the Fibonacci numbers. And so all we have to actually show is for n is equal to 0 and 1. This evaluates to 1, and for n equals 2 and afterwards, the recursive property holds that an plus 2 is an plus 1 plus an. So now let's try to see how it works algebraically. Alright, let's begin. And the property we're gonna use for the choose function, it's recursive property. We're gonna write algebraically. It says that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Now we're going to apply it directly here. And actually, before we're going to do that, here it assumes that k is bigger than or equal to 1, as we can't have something negative in the choose here. And because the initial value here has n choose 0, we're going to have to write it on its own and choose 0 plus the sum as I goes from 1 to infinity of n minus I choose I. And now we can use this property and we won't get into any weird stuff like something n choose negative 1. And so this is going to be n choose 0, which is 1 plus. Now from this property, we get this is plus the sum as I goes from 1 to infinity of n minus 1 minus I. Choose I plus the sum as I goes from 1 to infinity and to infinity of n minus 1 minus I. Choose I minus 1. Alright, now here, this almost looks like the sum if instead of plugging in, we plug in n minus 1, except it starts at 1. But if we plug into here, I is equal to 0, we get n minus 1 choose 0, which is 1, meaning that we can turn this one into n minus 1 choose 0 and add it into the sum as the I is equal to 0 place in the sum to get that this sum is the sum as I goes from 0 to infinity of n minus 1 minus I choose I. And now here we're going to do a variable change. And so we're going to replace I with I plus 1. And this makes it so that I plus 1 is equal to 1. So I is equal to 0. So it starts at 0. And then I plus 1 at infinity. And I plus 1 is at infinity, or goes to infinity. I also goes to infinity. So this sum still goes to infinity. Then here replace I with I plus 1, and we get n minus 2 minus I, choose I. And now, if we call this Sn, so this is the series, this is Sn, this is precisely Sn minus 1, and this is precisely Sn minus 2. And so we got the recursiveness of the Fibonacci numbers. Now we just need to show the initial values are 1 and 1. So S0 gives us the sum as I goes from 0 to infinity of a negative I choose I. And when you have something negative, choose something positive, it's this negative I choose I. Okay, alright. So this is going to be, like we said, on the diagonal in Pascal's triangle. It's going to be just the first term, and then the rest are zeros because they're empty spaces. And so this will just be the top number in Pascal's triangle, which is defined as 1. And then S1 is the sum as I goes from 0 to infinity of 1 minus I choose I. And again in Pascal's triangle, that is 1, 1, 1, and then 1, 2, 1, and so forth. And it's going to be this term plus the rest that are empty spaces, and so are zeros, and therefore are zeros. Namely, that means that we have this is just this first term here, which is 1. So the initial values are 1. Each number is the sum of the two previous numbers, and so Sn is equal to Fn, where Fn is the nth Fibonacci number. And there's actually, if you want to go even further with this, there's the formula for Fibonacci numbers, which is the golden ratio. It's the power of n minus negative 1 over the golden ratio to the power of n over square root of 5. The answer of these are the Fibonacci numbers is satisfactory enough But if we want to get an actual formula that works for all n, this is the formula. So these sums are just the Fibonacci numbers. And finally, that's it. If you want more content like this, please subscribe to my channel. And we'll be uploading more interesting content and things like this in the future. And finally, that's it.